My name is Félix Pérez. Today we are doing this webinar about free energy, our new feature in RatedPower. We are going to wait for about 2 minutes for everyone to join, and then we'll start. We are waiting for 1 more minute. Okay, we'll get started. Okay, so again, hello everyone. My name is Félix Pérez. I'm a principal software developer at RatedPower. And today we are doing this webinar about free energy, the new feature in the software we just launched. So like I said, I'm a software engineer in RatedPower. I have been in the company for like 8 years now. So yeah, you have my email and everything. If you have any questions, feel free to email me. Right, so let's get started. What is 3D energy? 3D energy is a new calculation model in RatedPower. It's a new type of simulation, which is an energy yield calculation, right? It allows you to estimate the energy yield of a PV plant. It's an entirely new simulation in RatedPower, which uses ray tracing and an advanced electrical model, and it has as well a terrain-aware backtracking algorithm to get you improved yield estimates, which consider the impact of terrain. It is better at estimating the backface irradiance because it uses ray tracing. And it's also better at estimating the electrical shedding losses. So, you know, the loss due to the impact of bypass diodes and the sub-layout of the module than previous models. We are also giving you a new 3D map view, which you can use to analyze the results. It is very challenging to interpret and do the analysis because of the amount of data that this simulation produces. So we had to design an entirely new interface just for the analysis, right? So I'm going to show you that. Yeah, of course, why did we develop this model? The reason is that in the past 5-10 years, right, PV plants have been getting more and more complicated as we have run out of the easy flat terrain that we had in the past, right? Nowadays, PV plants are in more and more complex terrain with different features. We also have things like terrain-aware backtracking, which it's super challenging for regular energy yield models to account for that. So we needed a new calculation model, right? And bifacial as well, it's a challenge. So that's why we needed to answer this necessity, right? So without further ado, I'm just going to show you how it works. First, I'm going to show you how you run a 3D simulation in RatedPower. It's super easy to use. When you are in design process, which is the screen in which you set your PV parameters, right? So this is the design process page where you will set, for example, the pitch, right? So say I want to change the pitch of my PV plant, say 5 meters, or if I want to modify the DC-AC ratio, right? We do all of that. We click Run Design to get results. We can see the new layout with structures and the peak power and all of that, right? We now have this new button here, which is the Run 3 Energy button, which you can click that and you start a 3D simulation. What's cool is that there is no new data you need for the 3D energy simulation. RatedPower gets the elevation data automatically for you. We get meteorological data automatically. We generate a layout internally, right? Which is the layout you see here, which is already in 3D, right? So this is already considering the real terrain data, the position of the piles, the position of the trackers, all of that. And this is already in RatedPower. We also have the electrical model, right? A very detailed electrical model with the section of each individual cable. All of that gets automatically passed to the 3D calculation model, right? So it's super easy to leverage this new calculation model. You don't need any new data that you need to add in RatedPower. There is only one input that is new for the 3D energy calculation, which is the backtracking strategy. As you can see, you can choose between terrain aware and flat backtracking. This is super useful to compare the simulations so that you can estimate the production gain from using terrain aware backtracking, if any, right? But that's it. That's the only new input. So yeah, let me show you. Like I said, running a 3D simulation super easy. You just click the continue button and the simulation starts. Now, as RatedPower users, you will see something new, which is that now you have two simulations out of one click of a button, right? We got the normal PV simulation and the 3D energy simulation. The reason for that is that the normal PV simulation has to run, and then that will start the 3D energy simulation, right? And so you get essentially two cards in your project page, one with the PV simulation and one with the 3D energy simulation. The 3D energy simulation itself, you can track the progress here. You can see right now it's in 2%. If you click view progress, you are redirected to this view where you can do essentially a better tracking of the progress of the simulation. Simulations take anything from 10 to 20 minutes usually. It depends on plant size and other factors. But it's been fairly consistent so far in that regard. Usually 10 to 20 minutes, you get your results. We are not going to wait, obviously, for this to finish. We have other examples. So as you can see, it's super easy to use. I think this is, it's a big deal, right? Being able to launch a simulation with ray tracing, with an advanced electrical model so quickly. That's new, essentially, right? So it's super, it's great that you can do that. The amount of, the depth of analysis you can do is super in-depth, as I will show in a moment. So we really think that this is an important thing for the future, right? That you can use it easily and that you can also easily apply modifications. So for example, if I decide that I need to modify the pitch in this simulation, right? I can clone the simulation using that button. Then you change the distance again, right? Say back to 6 meters or whatever. And you can run the simulation right away without needing to do anything else. The layout is automatically recalculated and you will get your new simulation. So with that said, let's say the simulation finishes, right? And now it's time to look at the results. So we're going to analyze this simulation maybe. This is a fixed structure simulation. And when you load the 3D results page, this is what you see initially. So you get a 3D layout with it's essentially the same 3D layout that we saw earlier from in design process, but the colors are different. And I will dive in that in a second. We also have here the KPIs and results for the simulation. So you have the production that the model estimates, the performance ratio. We have the system losses. The system losses are similar to what you are used to in RatedPower or PVCs or other softwares, but they are not exactly equivalent, right? And some of them are estimates. The concept of estimate is important to interpret the losses in 3D energy. Some losses are not part of the calculation model. So for example, here we have the transposition gain POA estimate. This is a calculation we do that is outside of the ray tracing calculation, right? This is not part of the main ray tracing calculation model. And it is only here to help you out in understanding the results. If we compare the POA values to the output of the ray tracing, we get what we call a shading loss, right? Because the difference would be attributable mostly to shading. And the same is true for the electrical model, where we have some estimates here, but the real calculation model output is what we call the shading and electrical mismatch loss. This is the actual result of the one diode model. This is so that you can use these losses to improve your design, right? So for example, if you have high shading loss, if you have high temperature losses or shading and electrical mismatch loss, you can take that information and improve your design with it. So yeah, then starting from here, more or less, the losses are fairly equivalent to any other simulation in energy yield. It's just the ray tracing that's a bit more complicated, and the electrical calculation model as well. We also have here the monthly values, and you can see them in a chart, which is useful. Now, the big star of the show here is the map, right? In this view, we are using colors to represent numerical results. So, for example, if you have different PV modules which have different irradiance values because they are less shaded, or maybe they are higher up in the structure, or maybe they are in a front row structure, they will show up in green, right? And if they are shaded or they have worse irradiance, they will show up in red. You also have a histogram here. I will explain the histogram a bit more throughout this demo, but the idea is that the free energy results have a lot of variability in them, so it's sometimes useful to think of the distribution as a histogram, right? And to try to understand that as well as what you're seeing on the screen. Because you may have just a few modules which are super shaded for whatever reason, right? And that may show up as a tail in the histogram, and that's easier to spot with a histogram. And we also have this feature, which is remove outliers, which what it allows you to do is that it removes the P5 and the P95 from the colors in the map, right? So this is better to understand the what are most of the modules doing, right? Instead of the colors being displaced by just a few tails in the histogram. And that will make more sense in some other layers. In this simulation, it's not so apparent. I will now highlight the thing about modules, because we really are showing you results per PV module, right? And you can see that here. We see that the top row of modules, this is a 3-portrait structure, right? The top row has higher irradiance than the middle row and has higher irradiance than the lower row. And furthermore, you can see how it's being highlighted on the screen right now. If I click, I can actually see the numerical results per module. This is super cool, right? You can actually see the production of an individual PV module in your PV plant. And then you can compare it to the neighboring modules, right? So say we want to compare the lower row to the middle row, and then to the top row, and we see how the production and the irradiance increase and change when I do that, right? And there are a lot of different values here. We have things like the shaded fraction, right? So this is the a proxy of the shading loss, essentially. We have the bifacial gain. We have the back radiant exposure. This will be your back phase irradiation, right? If we switch layer, and you do that here, this is the list of layers that you have, you can switch to back radiant exposure, and now you get the heat map for the back phase of the modules. So it's crazy the granularity you get with this, right? You can actually see how the modules in the edges of the structure are perceiving much more back phase irradiation, right? In this case, 155 versus 59, so it's more than double, right? Comparing the modules in the edge with the modules on the center. And we can also see differences structure to structure, right? So for example, if we compare these structures which are in the back to the ones in front of them, this module has a back radiant exposure of 120, more or less, compared to this one having 104. So you see how granular the model is. And this is all about giving you a more accurate result, which is considering way more detailed than before. Of course, this is what we call the edge effects, right? And they are something that in regular energy yield models we can't model very well because of the simplifications we have to make. But we are using a ray tracing model, and we are doing that for every single PV module, right? So it allows us to consider, for example, the impact of having a void in here, a gap between the structures, right? And these structures will have higher backphase production than the ones that are in the middle of the field, right? And you can make many different analysis and decision based on this. It's essentially like there is so much optimization you can do with this information, right? The idea here is that you have the information and you have the analysis tool to leverage that and to make decisions based on all of this. I'm going back to the front radiant exposure layer because I also want to show you how you do slope analysis or slope impact analysis. So let's say we are looking at this PV plant and we want to know the impact of slopes. We can start by clicking remove outliers, right? And then we see the colors. And in this case, we see a lot of green here. So all of these modules are producing more than the average, let's say. Then as we move back, we start seeing a lot of red, right? And this means that these modules are producing less. Now, the reason is super obvious, and you obviously didn't need a ray tracing simulation to know this. The reason for that is that these modules are in the north-facing slope, right? While the ones on the front of the PV plant are in a south-facing slope. And again, you didn't need 3Energy to know that, right? But what you know now is the impact, because you can quantify how much production you lose. If you click here, for example, we can look at this particular module. We see that the production is 1389 kilowatt hours, right? If we move to a module in the back, a second, right, and we click one of these, we see that it's 1118. So it's around 200 kilowatt hours less than the ones in the front, right? So there is a huge impact in there, in production. Another cool thing that we have for fixed structures and east-west is that you can actually display a shadings animation, which also explains this. So you click this button here, shadows, you enable the animation. You can choose the day and the time here, and you can move around the slider to change the time. So it's now super apparent why we are getting so much shading here, right? And so much production loss compared to the front of the PV plant here, where we essentially don't have shading, or not as much, right? Like if you see right now at midday, we don't have inter-row shading in this south-facing slope, but we do have it in the back. It's important to highlight that the shadow animation is not part of the ray tracing calculation model. It's on the side, right? This is calculated using your own PC in your browser. So this is not an output of a ray tracing model. This is just a tool to help you understand the results you get out of the ray tracing simulation. So yeah, I will also show you now some other layers. This analysis I show you with the slopes, it's easier to do with a layer we have, which is per table. So if you show the front radiant exposure per table, it's much clearer, right? And you may wonder, well, why didn't you show that from the beginning? Well, I wanted to show you the modules. I wanted to show you the granularity of actually being able to tell that it's the lower row in the structure that's actually more affected, right? But you can see it clearly here as well, especially if we remove outliers. We see how it's this back area of the PV plant, which is particularly bad compared to the front. Then we are going to transition into the electrical system. So we have, for example, the electrical shading loss estimate. This is per module. And this is showing us the impact of shading, right? So for example, here we have some partial shading going on between this structure and this one, because the structure here has a higher elevation. It's like overlapping a bit, right? It doesn't overlap, but it's higher. And this has an impact on shading and on the electrical production of the module, which is not proportional to the shading loss, right? This is a useful tool to identify issues in your layout, which are deeper than just a shading loss, right? And this will have an impact as well, depending on the stringing, so how the models are connected together, and the MPPTs. So all of that will be impacting this loss. We have then going on, continuing through the DC system, we have the voltage drop percentage per cable in the PE plant. So in this case, all the strings look good except for this one, right? So something's going on with this string. And if we click, we can see that the voltage drop is 0.6% compared to neighbors which have 0.005, right? So this cable is probably going around and doing something weird with its path, which you will need to correct. This is what we consider more a layout, like rated power layout error rather than a free energy error, in the sense that this is really what the string cable is doing, right? It's going around something and it's having to take a long connection. Probably looking at this layout, this string is connected to something over here, which it shouldn't be. But that's something that we are continuously improving with the layout in RatedPower, right? But yeah, I wanted to highlight that you have the losses per string cable, right? Which is super, like it's a lot of detail. We also have the the table losses. So this is a different aggregation level. We are now showing results per table instead of per module, right? So that's where you have the one from before. You also have the front POA radiant exposure. So this is the plane of array radiance on each individual table, which is usually, it's mostly due to misalignment in the table. So for example, here, we can see that the issues that the tables are looking west, right? And so that's causing a bit of loss in POA compared to the ones near them. Then finally, let's move on to the inverter. So here we can see the clipping loss per inverter. There is not much interesting, there is nothing interesting going on here. Essentially, we have a bunch of string inverters with different DC-AC ratios, and that has an impact on the clipping loss. It is interesting, however, that I hope you can see that, but these structures in the front are more red, let's say, than the ones in the back. And the reason for that is that these structures are in a south slope. Their production is higher than the ones in the back, and so you have higher clipping loss. So we have been half joking for a while now that with re-energy, you may be able to do DC-AC ratio optimization based on slopes and shading. You may want to have higher DC-AC ratio in the back and lower DC-AC ratio in the front in this PV plant, for example. That's the kind of improvement you can make with this tool, right? You can actually tweak the layout in ways which you wouldn't do otherwise. We also have the voltage drop for the LVAC cables, and in this case, the layout is looking better, except for these structures here, which have higher low voltage AC V drop of 1%. And it's probably because these inverters are connected to this power station, and maybe the cable has to do something like this, right? And it's not optimal. But you can spot, the cool thing is that now it's easy to spot that layout error and make the corrections that need to be done, right? Now, this was a fixed structure simulation. I'm also going to show you a tracker simulation. This is a PE plant where we are using trackers and we are using terrain-aware backtracking. And in this case, the shadings animation is disabled for now. We don't have the shadings animation for trackers yet. But the cool thing with trackers is that you get to see the backtracking impact. And we have a few layers for that, which are here: average, dawn tilt value, day tilt, and twilight tilt. Now, what we did here is that we took the tracking angles for every hour in the year, and we separated the values by beams, essentially, where an interval, which is day, is defined as an interval where the sun height is less than 20 degrees, and that will be mostly looking to the east, right? And then the twilight is the same thing, but at the west, and day is everything else. And so if we enable dawn tilt value, we see that we have values ranging from 12 degrees, more or less, negative, to 60 degrees. Now, 12 degrees negative is essentially looking west, right? So you might say, how is it possible that some trackers are looking west in the morning? Well, the answer is that they are in west-facing slopes. So all of these trackers, which are in a west-facing slope, as you can see here, are tilted towards the west in the morning, right? And that's the rain hour backtracking doing its thing, right? And we also have the opposite situation here, where we have these trackers in green are in a super, this is a high slope looking towards the east, right? So they are very green, indicating that they are almost true tracking, right? And you can see the same thing for the afternoon, and it's more or less the opposite, right? But of course, there will be differences. And so you see how in 3D Energy, we can manually set the tracking angles for individual trackers. And that has an impact in POA, has an impact in the production, and it has an impact in the production of each individual PE module, right? We may also even have situations where the terrain over tracking is failing a bit because sometimes shadows can't be avoided, and that will have an impact in the PE module production, right? So as you can see, when we look at POA, for example, it's also easy to identify that maybe we have some trackers which are tilted towards the north in this case because of terrain. So that's also easy to identify and spot and say, maybe I need to do something in this area of the PE plant to correct this issue. Right, so there is a lot of information here, and this is even, I'd say that even we need to learn how to use it, right? There is so much you can do with this information, and we need to understand like what is the workflow, what is the analysis you can, what is exactly like the most useful workflow for this, right? But I think that's something that with time, right, we will learn as users of this tool, how to leverage all of this information to improve our designs, and of course as a yield estimate to obtain financing in our projects. I also wanted to show you first I will show super quickly the layout editor. You can make modifications to your PE plan. So for example, say these structures which were here, I don't want them because they are tilted toward the north. I can do that, right? Remove them. And now I can run my 300 simulation right here. And that will start the simulation all over again without these trackers. So it's super easy to make very detailed fine tuning of the simulation. I'm using layout editor and 3D Energy. We really think that they are features which synergize a lot in the sense that the depth of analysis you get from 3D Energy can be leveraged very effectively using layout editor. And finally, I want to show you the documentation that we produce for each simulation. So we have an energy report in docx and PDF. You can edit the report. The documentation is only available in English right now, but that will change in the future. This is the energy report, and it's different from our previous report in that it has more hard data numbers, let's say, and it's more to the point of what's important, right? It's more summarized. So you have the production here. You have a table with the losses. This is the same as in the interface. You have the results per area with performance ratio per area. We think that this is something that it's super useful to really understand if you have a bunch of parcels, right, and you want to maybe understand which ones are producing more. This is super easy, right? You have the production per power station, and these are the power station codes from the layout. You have the production per inverter, including clipping loss and their DC-AC ratio. And then you have the inputs, same as which are the summary of how the simulation was executed, right? And then a few details of the PE plant itself and the electrical system. So this is a useful way to look at your simulation, right, in a more summarized way. We also have, I clicked the wrong button. We also have an Excel file which has essentially what you see in the 3D map, but in Excel in numerical form, right? So we can download the document here. Let's open it. And this Excel file, it has so much information in it. It probably has even more than in the map view. You have a summary you have the hourly values. So this is the production in each individual timestamp, right? And you have then, there are different sheets for different equipment types in the PV plant. So you have results per table. Here you have, for example, the POA radiant exposures of plane of array. You have the shading loss for all of them. You have individual PV module results. You have individual cable results, where you can see the loss for individual cables, right? You have the MPPTs, so you can evaluate voltage window modification in each individual MPPT. You have inverter results. You have the results per power station, and you have the backtracking results, which are for individual trackers in the PV plant, the values you saw in the interface. So lots of information to digest here, super useful for in-depth analysis. And finally, you have an AutoCAD, which is essentially the same thing you see here in the interface, but in AutoCAD for so that you can share it. It's not all the layers are in the AutoCAD, so it's a subset, but it's still useful. And you also have GLTF files. This is a format you can download, and it's essentially a 3D model, right? And in Windows, you can open them. You can open them directly using 3D Viewer, which is an application in the Microsoft Store, and you can just it's a downloadable file, right, with the same results as some of the results of the interface, which you can then share with someone else through email or whatever, right? So it's useful. So, well, I think that's about it. I'm almost over time right now. So, yeah, I hope you enjoyed the walkthrough. I know it's a lot of information, but it's also a super cool tool and feature that we hope you will enjoy using. I also want to mention we published a validation report where we compared the results of this calculation model with real PV plant production. And I really would like you to download the report and read it to see the results, but it was super close. We had we unfortunately only have 2 PV plants to compare against, but in those 2 case studies, the error was lower than 2%. So we are super happy with the results. I'm also going to take this chance to ask if you have real PV plant data that you can share and you would want to collaborate with us, please contact us through my email or any other channel, because we really want to find more data so we can validate the model further. So with that, we are going to go to Q&A. And I already have a few questions here. Yeah, I'm going to start. So the first question, I'm going to go by the chronological order, okay? So we have the backtracking algorithm. Is the backtracking algorithm related to the tracker selected? Which SAT informs the terrain tracking option? Right. The backtracking algorithm is done tracker to tracker. So it's essentially we look at one individual tracker in the PV plant, and we compare the position of this tracker to its neighbors, and we calculate the slow power backtracking corrected angle with that, right? So it's always individual per tracker, considering its neighbors. Let's see. Benchmarking studies, yes, the evaluation report is what we have for now. We think that we will have more studies in the future. 3D design with the random downloadable can be uploaded for PVsyst. Yes, you can download the PV colada file in the regular PV simulation. And the PV colada file has the terrain mesh and all of the trackers and structures in it. Yeah, that's not new for this feature though. This is part of regular RatedPower. Is the backside irradiance calculated in 3D? The answer is yes. We are using ray tracing for the back face as well. That includes ground reflections. And we also have a detailed shading model, which we simulate the back face irradiance with the presence of torque tube and piles. and we apply that as a constant loss throughout the simulation. And like I showed earlier, you can even see the edge effects, which come from considering the backphase irradiance per module. For example, in the case of these two trackers, which have no tracker on the left or on the right, you can see much higher backphase irradiance than neighbors. So it's per tracker, per module, and considering ground reflections. What else we have? Right. Is the backtracking algorithm taking into account 2 or 3 points per tracker? It's only considering 2 points. One going from, it's 1 point in this tracker and another point in the other tracker. While we were developing the calculation model, this is something that we looked into, and we didn't find that it improved the result a lot, changing how many points we consider. But it's something that we will be looking into in the future for further improvement. Essentially, at this point, like there may be some small tweaks we can make to the algorithm, but it's not going to improve things like another % in improvement. It's maybe going to be like very little change. Right. Does it work for east-west simulations? Yes, you can simulate with east-west. I don't think I have a simulation to show right now, but it does work perfectly well with east-west. Yeah, you can also see a shadings animation there. Let's see what else. Right. Can we read the result of plane of array irradiance for an individual tracker? Yes. You can see that in the interface right here with front POA and also back POA. You have to take into account that this does include the impact of terrain over backtracking. So, of course, depending on your tracking algorithm, that will be different. And you also have these results in the Excel file as well. What else? Modules with higher yield should be colored red and those with lower yield should be colored in blue. A red to blue color scale is more indicative, I suppose. Thanks for the feedback. You can change the color schemes. You have a few different ones here. Here you have the plasma color scheme, which is better for daltonic people, I guess, I suppose. Okay, color blind, sorry. And you also have the gradient cool, which I think does what you want more or less. The well, not really, because it's lower in blue, so it's not exactly the same. But yeah, also we researched this while we were in development, and we found that people tend to associate green with better and red with worse, kind of like you do with the traffic lights, right? So that's why we went with this particular version and not something else. But thanks for the feedback. We can. It's relatively straightforward for us to add more color schemes, so we will look into that for sure. What else? Is this a tool to model terrain following trackers? Right now, no. We are not able to model terrain following trackers in free energy and really in RatedPower, and we don't support terrain following trackers in RatedPower yet. We do have this in our roadmap though, and we plan to implement it in the future. What is the activation of bypass diodes? Right. We have this layer here, which is right here, activation of bypass diodes. And this is essentially, it's kind of like an internal thing of the model that we are exposing. We are counting every time a bypass diode gets activated in a PE model, and then showing you that here. But this is not an easy layer to interpret, really, because the thing is that you may have shading, but that doesn't necessarily mean that you will have bypass diode activation, right? This is more related to having issues with the individual PE module where the model is detecting bypass diode activation, and that can happen because there is a shadow of a particular shape in it that's maybe covering maybe less than half of it or whatever, right? And yeah, this may also happen depending on what the rest of the string is doing as well. So it's not a super straightforward layer to analyze, and this is one of those where we need to learn to interpret it. Like we need, us meaning RatedPower, we also are trying to understand better this result and how it translates into model performance, because it's not super easy. But we did think it was interesting to show that. Um, then is this methodology able to model 3D backtracking algorithm? Yes. And if yes, which is the goal for these algorithms? To avoid shade, maximize POE's irradiance? I think that the goal can be summarized as avoiding shade. It's trying to limit shading as much as possible or remove it. It doesn't have any other goal right now in the algorithm. You can select flat backtracking as well, and you will have true tracking soon for thin film modules. What else? Can I import DWG layout file to your software? Unfortunately, no. That's not possible right now. It is in our roadmap. We are looking into how to implement this feature, but it's super challenging for us as software developers, essentially, to do well and properly and in a way that's user friendly, right? But yes, absolutely, we have it in our roadmap, and we think that it is another feature that would synergize very well with free energy. So we are very aware of the necessity. Thank you. How do you simulate the real irradiance? We are using ray tracing. I forgot to mention, we are using Radiance, is our ray tracing engine. It's a lighting simulation tool which is well known in the PV industry, and that is what we are using for the ray tracing calculations. How much time will it cost when we simulate a 100 megawatts project? Around 10 minutes, in my experience. Usually, to get to 20 minutes, you have to be in like the 200 megawatt range onwards. We do have a peak power limit of 500 megawatts DC. That's the maximum you can simulate with free energy. So 500 megawatts. But up to that point, it's still like 10, 20, 30 minutes. I think that the slowest simulations I have seen are like 450 megawatts DC peak, right? And that's 30 minutes. So it scales fairly well. It's enough time to get a coffee. Is a resolution of 3D terrain model display governed by the user topographical data uploaded? Yes, but it's complicated. You can upload topography data in any resolution. I think that the limit is just that you have to upload in a CSV file and the maximum size is 500 megabytes. That still allows you to get 1 meter resolution easily. And that's the terrain model that is used in the simulation and in free energy too. However, that's not the same mesh you see in the 3D view, and this mesh can't get simplified if it has too many points. So that's something to keep in mind. This mesh may not exactly be the same one you uploaded, but it will retain most of the detail in it. What is the granularity of the terrain data used for RatedPower? Right, you have an automatic source, which is Google Maps, that can have a resolution of anything from 3 to 5 meters up to 10, 15 meters. That changes with plant size. So the larger the PV plant, the higher like the resolution is, right? So for I don't know, 300 megawatts plant, you may be looking at 10 meters in resolution, versus a smaller PV plant, you may be down to 2 meters, right? Then that's for the automatic source. If you upload your own topography, like I said earlier, you don't have a limit. Essentially, the limit is 500 megabytes in the CSV file. Are you able to modify the terrain to show areas that have been cut and filled to reduce the slope? Yes, earthworks. So you can either upload terrain which has been modified in like a custom terrain, or you can use the earthworks feature in RatedPower, and that is taken into account for the free energy simulation. However, our earthworks feature produces flat platforms, which are very large and cast shadows on their own, so it's not super optimal. But yeah, you can consider the modification of terrain. Is it possible to perform simulations with hourly timestamps? No, unfortunately, no. Right now, the simulations in hourly resolution take, like I said, 10 to 20 minutes. Sub-hourly would multiply that by the amount of extra interval, right? So if we are doing a simulation in 15-minute steps, that will mean 40 minutes of simulation time. So that's why we don't have that right now. yeah, it's possible that in the future we may have it, but not as an option right now. Would you be looking in the future at automatic layout optimization based on the 3D model? That's a good suggestion. We have thought of implementing essentially tips for the user to improve their layouts based on 3D results, but I don't think we have been thinking about an automatic improvement. We do have in our roadmap the variable pitch, where the pitch is automatically modified based on slopes, which I think is what you want to do like at least 50% of the time, right? Especially for fixed structures, but that's still in development. So yeah, right now you have to do those modifications manually. We are out of time, but I will continue answering the questions because there are just a few of them left. What influences the performance of the simulation the most? Can you run simulations with 15 or 1 minute data or several years? Right, so I answered several timestamps. What influences the performance of the simulation the most is the number of modules, so size of the PV plant. That increases the number of ray tracing sensors we have to run. So that's an issue. And then if there is a lot of shading, that has an impact on the electrical calculation model, and it increases the simulation time of individual PV modules. Because when a module is uniformly illuminated, right, there is no shading, we just run the calculation model for the one diode model once per module, right? But if you have partial shading, we may have to run the calculation model, the one diode model, like 6 times or 8 times per module that's shaded, right? So that increases the calculation time a lot. But I'd say that mostly it's PV plant size. The renewable tracking doesn't have an impact, for example. So yeah, in that sense, it's pretty cool. Also, like the ray tracing for the back face is way slower than for the front face, because for the back face we have bounces, which we have less bounces for the front face. So in terms of the ray tracing time, maybe it's something like the front face takes 30% of the time, the back face takes 70%, which is kind of crazy, especially if you consider like how much production is tied to that 70%. But yeah, it's what it takes to run the proper ray tracing simulation with the required number of bounces for the back face. Can I change the backtracking behavior? Like simulate with no backtracking, all rows with the same angle and ideal angle? Yes, you can do that. It's in the energy inputs. You can simulate flat backtracking, and it's useful as a comparison. Running the comparison, we have seen increases in production of like 2 to 5% using terrain over backtracking, of course, depending on the terrain. Use GPU or CPU to calculate? Interesting question. The answer is CPU only. We are not using GPUs for this calculation. And that's because Radiance, which is our ray tracing engine, is CPU bound. So CPU only. And please, can you start with the Verland for us to see? I don't have the time, sorry. Please contact customer support so that you can get a demo of how this works in Verland. And finally, can we get a recording? Yes, this webinar is being recorded and will be shared in our webpage. So I think that's all questions. I somehow managed to get through all of them. So we'll leave it here. Thank you so much for attending. Thank you so much for participating. It was great answering all of your questions. And I hope that you will run 3D simulations in the future and that you will enjoy the results. Thank you so much and have a nice day.